how loud is the sun? I know it's kind of a weird question because sound can't propagate through the vacuum of space in the same way that you can hear me right now. But let's just think about it as kind of a fun thought experiment. It's live. So the sun, just because of how much heat energy it's putting out into the universe and all the nuclear reactions, just fusioning hundreds and thousands of tons of material every single second, because of all that energy radiating out from the sun, you could think about it as producing a lot of sound at the surface, and according to heliophysicists, it does. It produces quite a lot of sound at the surface because of all the energy and reactions happening inside it. Now, they can't be sure on the numbers because the surface of the sun is very, very turbulent, and they haven't modeled everything perfectly, and there's gigantic magnetic fields that throw millions of tons of worth of stuff into the solar wind. Anyway, so at the surface of the sun, they estimate, some of them, there could be 200 watts of sound power per every square meter of the sun surface area. And that would equate to, if we were hearing it as sound, 329, yeah, I knew that off the top of my head, 329 decibels, which is loud enough to kill you on the spot. Isn't that fun? But what would happen if sound could propagate through space like it propagates through the atmosphere of Earth? What would happen if you could hear the sun all the way on the surface of Earth? Well, sound, like any other radiation, the sound waves, would propagate through space according to the inverse square law, which is to say, if they were centered on the sun here, as they came outwards towards Earth, if they radiated out in a perfect sphere in all directions, as they got further and further away from the point source of the sun, they would get further and further apart, the radiation would, which means even if you have the same number of watts, the square meterage here that they would have to cover gets larger, which makes the overall value go down. So you can see here, even at the center of the sun, it's higher, surface lower, you get all the way to the Earth, it spreads way out. Now, this is not to scale, obviously, but this distance is immense. It is 150 million kilometers. So according to the inverse square law, what happens when, by the time this 329 decibel sound, what happens to it, which would kill you on the spot, what happens to it when it gets all the way to the surface of the Earth? Well, this power value would be reduced to just 5 milliwatts per square meter, which equates to 96 decibels. Now, this would not kill you. This would be about what it sounds like if a motorcycle was constantly revving in your face, or someone was jackhammering inside your home. It would sound about like that, and it would be very, very annoying and bad, but it wouldn't kill you, wouldn't burst your eardrums. But just think about that. The sun is so far away. The sun is so far away in general, but it's so loud that even when it is 150 million kilometers away, it would still be loud enough, if that sound got all the way through the atmosphere just fine of Earth. It would be so loud that it would be, you'd have to wear ear protection if you were, just in its presence for long enough. It would be close to deafening, right? Not like actually deafening, but it would be like being in a rock concert all the time. It would be very, very irritating and annoying. That's how loud the sun is, if that sound could get all the way to Earth, which should give you some kind of appreciation of just how powerful the sun is. I know I have it. Hello, and welcome to another edition of Because Science Live, the live version of the show on this channel where I take all of your nerdy comments, questions, and corrections live off the top of my head. Look, I'm not an expert. I'm not a scientist. Sometimes I come up with fun little thought experiments for us, but I don't know everything about everything, so if I don't know the answer to one of your questions, I will say I don't know, and we'll go on to the next one. But I know a little bit about a lot of nerdy things, so if you have anything nerdy, sciencey, pop culture-y, hit me with it, and I'll give it my best shot, which is not a song lyric. I have Nate here. Nate?
Hey.
Nate?
It's Nate's birthday. So he's out today. He's left the void.
Oh. Does time flow the same way in here? Doesn't matter.
You know better than anyone. It's your void.
What do we got?
C.F. Geldstrom asks, if something was at absolute zero, would the universe cease to be?
If something was at absolute zero, would the universe cease to be? Well, if a single thing, an object, was at absolute zero, I don't think it would cause the universe to die. But I think maybe a better, or a more realistic interpretation of what you're asking is that if the universe started approaching absolute zero, would the universe end? And that's kind of that's a very hard question to answer, but I think what it's getting at is the so-called heat death of the universe. So as the universe expands, and it expands at an increasing rate, which we now know that it is, thanks to observing galaxies and how they move away from us and how the light changes as they move away from us, the redshift, if you want to look it up. Because of all that, things are getting further and further and further apart. Eventually, things will be so far apart and all of the stars and all of the galaxies, everything will run out of their fuel. Eventually, things will be so far apart and so cold that the universe as we know it will not exist in the same state. It will be dead for all intents and purposes. For life such as we, there won't be a power source like the sun to sustain us. Everything will just be cold and dead. Right now, the average temperature of space is just 3 Kelvin, and absolute zero is 0 Kelvin. So it's not that far away. But eventually, if the heat death of the universe theory pans out, it'll be billions of years from now. We'll be long gone. But if that pans out, then everything will be so cold, so far away that life as we know it would have to cease to exist in some interpretation of that word. The universe would still be here, right? I mean, the universe is everything, so it would still exist, but for beings that need energy and stuff in the universe, it wouldn't really exist in quite the same way. So, yes, if the universe approached absolute zero, it would not be the same livable place for us. And it's not even livable that livable right now. Think of the fraction of Earth that we can survive on habitably. Now think of the fraction of planets in our solar system that are viable to live on. Now imagine the fraction that are viable in the galaxy, given those numbers. The universe wants us dead. We are a miracle of happenstance. Just a biofilm thinking about how much it's stuck onto a rock, floating through space forever until it gets so far apart from anything else that I'm spiraling. Help me out.
Are you all right?
No.
Okay. Well, A.R. Schaefer 76 asks, is there a scientific way to prove the Mandela Effect?
Is there a scientific way to prove the Mandela Effect, which I believe, unless I'm mixing it up with something else, is the effect where there's enough people who believe something that there's like an alternate interpretation of reality, right?
Correct.
This is the Berenstain Bears situation.
Yes.
And I really dislike it. So would there be a way to, let me backtrack. Would there be a way to prove the Mandela Effect? I think there's, with Berenstain and Berenstain specifically, I think there would be a way to see how many books print, because I've seen, maybe it was Photoshop, but I've seen printings of both names. So you could do a survey of how many different printings were in how many different schools or were sold over time or whatever, and you could see what percentage, you could get an idea of what kind of percentages would be there to see. It's like, no, 20% of people who saw this book had this printing, 80% had this printing. So it makes sense that most people would interpret it this way or would remember it this way. So that'd be some way of getting at, okay, well, is this a false memory or not? What I don't like about the Mandela Effect is this weird implication that the universe must have been different because you remembered correctly. And it's so, oh man, it's like the height of thinking you're super awesome. It's arrogant in a way, right? No. It's Berenstain. The universe can't be correct because I'm correct. Right? Like, oh, there must be a parallel universe because what are the chances that I would misremember anything? Where are my keys, by the way? You know what I mean? So the chances that you are correct, even a number of people, the chances that a number of people retweeting that viral tweet that says Berenstain on the internet, what are the chances they're all wrong? Pretty good. Happens all the time. mass delusions, episodes of mass hysteria, grand cultural ideas about what is true or not. Until the 1950s, they were printing ads in magazines that had doctors' testimonials saying, well, Camel's is the only cigarette that I smoke. From doctors in magazines. An entire culture, an entire group of people can be very wrong about what is true, especially over time. So, yes, we can all be wrong about Berenstein versus Berenstain. It's much more likely than there being parallel universes that you just made up. I'm kind of ranting a little bit, but
Cool.
I mean, yeah, cool. Thank you. What's next?
The Quiet Show asks, what's your favorite chemical reaction or natural phenomenon?
Oh, okay. Favorite chemical reaction. I don't know if I could say it's just straight up my favorite, but one of the ones that I've seen recently that is very weird, you can look up on YouTube. It's by a guy called Niall Reed, Nerd Rage, I believe his name is. And what he did is discover there's a really weird reaction that happens with aluminum and mercury. And if you have aluminum, like an aluminum block here, and you take a dab of mercury and you put that dab of mercury on it, it reacts in such a way that it creates these tendrils that raise up from the aluminum and then have some kind of mass here. And it kind of looks, in real time, sped up a little bit. It looks like a jellyfish of metal is raising itself up from a hunk of aluminum. And it's really weird and really bizarre. It's kind of like the Pharaoh's snake chemical reaction, or just the snake if you've ever burned one on the 4th of July or what have you, and it kind of extends itself even though it's just a small pellet. It's kind of like that, but even weirder. I would look that up. Nerd Rage, I believe. Aluminum and mercury. It looks really, really weird. Check it out. What's next?
Orangitis asks, would you be able
What kind of disease is that, you think? Orangitis. Is that just a weird way of saying scurvy?
Or is it that you eat too many oranges?
And so you're inflamed from oranges?
Yeah. I don't know. But
Okay.
that's not their question.
Okay. Never mind.
Would you be able to hear in a nebula?
Would you be able to hear in a nebula? So after we did the Can You Hear a Scream in Space episode, which you should all watch, after we did that, some people were asking, well, could you hear in a region of space that has more gas than just the more devoid of stuff interstellar medium? And while it is true that a nebula is more gaseous than the surrounding space, it is still very, very rarefied air. And well, rarefied vacuum. So, I mean, if you were to go from the void into a nebula, I've heard it described by physicists that you wouldn't even tell the difference. Like, if you went from space to nebula, you wouldn't be able to tell that there was an edge to that. That's how wispy nebulae are. And so it follows then that even if you were inside of a nebula, you wouldn't be able to scream in the way that you can scream in Earth's atmosphere. You need something pumping out a note that is so low with wavelengths so long, something so massive that you can get these interaction distances that have to be much, much longer, light years long, like the black hole that we talked about was doing, where it was pumping out a sound wave with wavelengths in tens of thousands of light years or hundreds of light years. That's what you need for wavelengths such as we make. The nebulae are still way too thin and wispy for us to scream in them. So you need something more like a atmosphere. So go to Titan and sound like Barry White. Yeah. Okay. What's next?
Frog Lump asks, is human spontaneous combustion actually possible?
Human spontaneous combustion is not a thing. It has been reported, of course, for years. It is a very common talking point in, kind of pseudo-science-y, mystical, science can't explain this, that, or the other. But science can explain this, that, or the other. It's called the John Wick effect. I'm kidding. It's just called the Wick effect. Although the John Wick effect is after that movie when every other movie wanted to have long extended cuts of fight scenes without cutting between every punch like modern action films did in America. That's the John Wick effect. But the Wick effect is, and this gets kind of morbid, but hey, we're live. So the Wick effect is, let's say you have a a human body, which I will represent as a, as a sphere, as any good physicist would, and then you have that human body surrounded by clothing. What the wick effect does is it's basically imagining a human as a candle. And so the wick could be something like the clothing that is around you. So if you have now a source of flame, the flame would ignite the wick, your clothes or what have you, maybe something you're sitting on, and then that wick would start to draw up material to burn. Now, what material is it going to burn? Your fat and your flesh. In the wick effect and in spontaneous human combustion, what is burning is very slow burning human fat and clothing and bone and tissue. And it burns slowly. It doesn't, spontaneous human combustion is not a combustion. People called it that because when they found people who had succumbed to the wick effect, they had found people with just like a leg and then all of them missing, like they exploded in a combustion-like reaction. But they didn't. When you do experiments, you can find that if you have a small source of ignition, say a cigarette that you, backing up a little bit, these people don't just let this happen. These are sometimes people who are incapacitated. So say someone who passes out, blind drunk in a chair, has a cigarette and they pass out and they drop the cigarette on themselves. That cigarette starts their clothing on fire, which then slowly draws fat into that wick to slowly burn them down like a candle until only one thing is left. Maybe the only one thing that wasn't covered by their clothes, that wick, like a leg. See, you can prove these things and you can look into them more scientifically. I think spontaneous human combustion is very alluring as like a science can't explain what happened to this person kind of thing. But when you look into it, it can be gross, but it is a physical effect that we know about. It's called the Wick effect. If you want more information, search for that and then go watch John Wick. It's a pretty good movie. What's next?
JD asks, how strong would Captain America and Bucky Barnes' bones have to be to avoid jellification during the fall from the jet in World War II before they were frozen in ice?
That's so specific.
Okay.
Do you think I know how far they fell in that movie, in that one scene off the top of my head?
Just the jellification.
The jellification.
How would they avoid it?
Well, I mean, we can pivot here a little bit. I mean, I never want to think about vibranium again. It's such a weird substance because it tries to decouple two things that are coupled, like kinetic energy and momentum and things like that. And those two things are just intrinsically related. So when Captain America falls from a great height and then falls on his shield to shield himself from that impact, you have to really make a physics jump to say that wouldn't impart the same amount of force on him. It's a rigid object. It's not decreasing the amount of time it takes for him to come to a stop. No, it's not increasing the amount of time, rather, like an airbag would, the amount of time that it would take for him to come to a stop. So it's not going to lower the force. So that landing on Captain America's shield, unless you stipulate a magic material, landing on Captain America's shield is not going to prevent jellification, as you say. But you could think of it, I mean, I know neither of them had this, but if the super soldier serum that Bucky and Cap had somehow augmented the way that their bones were constructed, say they told the cells in their bones to start forming different kinds of lattices inside their bones. If you break open a human bone, we're getting pretty dark here. If you break open a human bone, it's kind of like a spongy looking lattice in there, kind of like you crack open a bone and inside looks like a loofah. It just does. And it's a loofah-like structure, but that structure, because of the way it's oriented, is very, very strong. That's why human bones are pretty strong given the material. So I can imagine the super soldier serum altering that in some way so that it would change the material properties of their bones, making them more resistant to breaking, more resistant to impact, tension, and compression forces. Maybe something like that. But if you wanted to get super specific, I would have to look at the scene in question because it's been a while. And how many Marvel movies are there? 20-ish? I got time for that. I mean, I do. It is my job. I'll get back to you. What's next?
Patricia G asks, are you scared of black holes?
Am I scared of black holes? It's hard. This is one of those theoretical versus practical things. If I was near a black hole, would I be afraid? Yes. Will I or any person ever be near a black hole? Probably not. I mean, the chances of, right now, with current technology and even speculative technology like nuclear fusion propulsion engines, those kind of things, even antimatter engines if you want to go further. Even with that kind of technology that's centuries off, maybe a century off, who knows? Even with that kind of technology, it might not be possible to get to the next star in a human lifetime. So the chances of us getting so advanced in our technology that we can go to the nearest black hole, which I don't know, is it in the Sagittarius cluster? It's much further away than the nearest star, which is only 4 light years away. It's much further away than that. So the chances of a human of humanity getting the advanced technology and then be able to travel far enough that they can get near a black hole and then start experimenting near it or around it and then be afraid of it, I would say exceedingly low. So am I afraid of a black hole? Theoretically, yes. Practically, no. I don't think anyone's ever going to be near them, at least not in my lifetime. But who knows how long I'll live for. What's next?
Forever.
Forever! What's next?
Buffalo.
I mean, I will. I mean, just...
The void, there's no time.
There's no time.
Or space.
And we're making videos that will be, cataloged somewhere eventually. I will outlive my corporeal form.
Ayo.
Ayo. What's next?
Buffalo Carnivore asks, can you create your own star by condensing matter to its possible limit?
Can you create your own star by condensing matter? So I could answer this in super depth, but I don't have to because there's a video that we did when we went to the largest laser facility in the world for a Fallout video. You can look it up on our channel. It's how powerful could Fallout lasers get, and that's the largest laser facility in the world. Now, what they do, this diagram kind of helps. What they do is they put a little bit of tritium and deuterium in a tiny pellet, literally less than the size of this little dot here. They put it at the center of a giant metal and concrete sphere that is, I think, 10 meters in diameter. So it's huge, 30 feet across. So it's huge. And they fire, they fire the largest laser array in the world at it. 192 beams come from all sides, perfectly aligned to laser down on one little bit of deuterium and tritium fuel. And what that does, the lasers obliterate the canister the fuel is in, and that bathes the canister in X-rays. And this implodes the fuel, and then what they can get is a fusion reaction. It's simulating the temperatures and pressures in the sun. And they do that at the National Ignition Facility. It's really, really cool. We're talking billions of atmospheres of pressure, something crazy. So we can use technology to create star-like reactions here on Earth. And it is a kind of a form of compression, right? Applying heat and energy to implode fuel down so that it undergoes a nuclear fusion reaction. So we do this on Earth. We bring the power of the sun down to Earth with technology. I can't think of cooler stuff than that. What's next?
Vasily Janulis asks, could we extract energy from the sun directly?
Like with solar panels?
Maybe like lasers?
Like laser. Where is Nate? Lasers.
I'm Nate.
Right. Sorry. Can you get energy from the sun directly? I'm gonna assume you don't mean something like a solar panel. So again, maybe this diagram here can be useful. If you are mentioning something like a theoretical Dyson sphere to go around a star, this is a more direct way to harvest energy. And what you're doing is getting out of Earth's atmosphere and then putting some kind of, let's just say, a shield around the sun that can absorb the most energy possible. Because just like we went through, this is all tying together, because just like we went through, the intensity of the sun gets more intense, the closer you get to it because of the inverse square law right here. This is by the time this is sound power, but by the time energy gets to Earth, it is like 1,000 watts per square meter. That's pretty good. It powers everything, all life on Earth. Not all of it, but most life on Earth. So it's pretty good. But at the surface of the sun, the amount of energy coming out of it per square meter is 63, I know it's on the top of my head. It's 63 million watts per square meter. It's a lot higher than 1,000, 63 million. So the idea would go, if you put, let's just say something like a solar panel, much closer to the sun, around it, in all directions. So you got more energy per unit area and all of the energy possible, because right now, the only energy hitting the Earth is just this flat plane. It's not hitting the whole Earth at once. That's why we have day and night. So if you could get around all of the sun in 360 degrees and capture all of that energy, you get a monstrous amount of energy. And that's why the Dyson sphere is so popular as a concept, especially in sci-fi, because with that amount of energy, imagine the things that a spacefaring civilization could do with this level of energy. They could, start colonizing a galaxy or what have you and get ultimate power. But So that's probably the grandest idea of harnessing energy directly from the sun. If you want to look it up, Dyson spheres, made popular by Freeman Dyson, the physicist. I'm sure that's his name. It is. Whatever. What's next? One more? I think we got one more.
One more? Do you want something kind of existential or something powerful?
Give me the existential one.
Do you think, this is from Junha Cal, do you think vacuum decay can delete the universe?
Oh, dang it. I don't know. I'm not an astrophysicist. I'm familiar with the term. I'm not familiar with the exact ramifications of the theory. Let's take the other one, because I don't want to speculate and point you in the wrong direction.
Okay. On that one. The Hades Nexus asks, how powerful can a solar flare get? Tying it back to the sun.
Whew! Good job, Nate. A solar flare, how powerful did they get? Well, again, I don't know the numbers for the solar flare power off the top of my head, but what I will say is that, again, consider the scale of energy that we're talking about here. The Earth is 93 million miles away. 93 million miles. You will never travel that distance in your entire life if you had 100 lifetimes. It's so far away. And even so, a burp of material on the surface of the sun, just a little bit, can travel all the way to Earth and could theoretically, wipe out the electronics in our satellites and mess with electronics here on Earth and wreak havoc with the power grid, for example. Just minor perturbations on the sun's surface can travel all this distance across space and then mess with stuff on our scale. The power of that kind of event should be very, very clear given the scale that we are talking about. When you have a coronal mass ejection, for example, just the tendril that gets thrown off, and then this is going to be not to scale again, but the tendril that gets thrown off from the material, the plasma that's caught up in the ever-tangled magnetic webs of the sun. The material that gets thrown off is this area is larger than the Earth. Incredibly powerful. If we were next to the sun and a solar flare happened, thank you. For watching another, look, I don't have all the numbers off the top of my head. Thank you for watching another edition of Because Science Live. Hope I did my best, pointed you in the direction of nerdy stuff that you can look up afterwards. Thank you for joining me for an entire week of Because Science. Next week, of course, new vlog, new episode, another live stream, and maybe a special announcement about an interesting large project that will be coming your way on this channel. I can't wait for you all to see it. It's going to be cool whenever it happens. So have a wonderful rest of your weekend. And you know, when you think about the scale of things, how big this is, how small we are, how just one of these events could wipe us all out, it gives you the sense that nothing matters. But as I was reminded by one of you on Twitter, when none of this matters and we're still here, everything matters.